8.4 is all about different theorems. And so we're going to kind of go through each one individually, discuss a little bit about what it means, and then maybe show some examples of those things. So the first theorem, this is the fundamental theorem of algebra, and it says that every polynomial function of degree n, with n being 1 or more, has at least one zero, even if that zero is complex. Okay, so this means that every polynomial function has a zero, but it could be that functions like this, they don't have a real zero, but they have a complex zero. So this is an example of a zero. There are two zeros in this case, but they're both complex. And so every polynomial, it doesn't matter what kind of polynomial, every single one of them will have at least one zero if n is 1 or bigger, and they may be complex. Okay, so what if I said I have three zeros, 1, 3i, and negative 3i? Well, how can I represent the function that comes from these zeros? Remember, zeros are always linear factors. In other words, it's always x minus 2, x plus 7. These are linear factors. And so what I can do is I can take these things here and I can go back to this. Well, what would the zero be if I have x minus 2? Well, the zero would be 2. If I have x plus 7, the zero would be negative 7. So I have to flip the sign and rewrite it in that way. So f of x would be equal to x minus 1, x minus 3i, x plus 3i. But if I want to include that idea of a stretch, then I just need to put this placeholder an in the front. And what this allows me to do is, if I want to say 2 times this function, I can have a 2 there. But that's not going to affect my zeros. And so let me show you what I mean with this function. If this function was multiplied by 2, all that would happen is it would stretch. The zeros didn't change. It just stretched. So this thing here is just the stretch factor, or the shrink factor, and these 3 pieces are our actual zeros. So anytime we're given numbers, we just have to go back to the linear factors to get our function. In this next part, I want to talk about both non-real and irrational zeros. And we'll just look at the non-real first. And so if we have complex numbers that look like a plus bi, where b is not 0, this complex number, if this is a 0 of our polynomial, then its complex conjugate is also a 0. So remember, the complex conjugate of this is a minus bi. So if this is a 0 of our polynomial, and b is not 0, then its complex conjugate must also be a 0. So if I'm given 1, the other also has to be a 0. Now, moving to irrational, that same kind of idea applies. If a plus c square root of b, where a, b, and c are rational numbers, and obviously b is not a perfect square, or they wouldn't have written square root of b. If this thing here is a 0 of our function, its conjugate is also a 0, a minus c square root of b. So it's very important to remember that if I have one of these two, because it works both ways, if I have this or this, then it tells me I need the other one. If I have this or this, it tells me I need the other one. And so let's look at an example real quick. If I have these 3 zeros, negative 2 plus 5i, 2i, and 1 minus 3, square root of 3. But my function is degree 6. So first thing I need to do is I need to write out the conjugate pieces for each of these. Okay, so a stays the same. So negative 2, positive becomes negative, negative 5i. Okay, here would be just negative 2i. Here, 1 plus square root of 3. Okay, now I have all 6 of my zeros, and I have to plug them into the linear pieces. So like I was doing before, f of x equals x minus, and I'm going to put this whole thing in parentheses, negative 2 plus 5i, x minus negative 2 minus 5i, x minus 2i, x minus negative 2i. So here, I didn't have to do x minus negative 2i. I could have done x plus 2. Here, I put the minus outside because I want you guys to see that you would have to distribute the negative. In both of these cases, you would have to distribute the negative. Okay, and lastly, I have to have these two pieces, but I didn't have enough room. So it's all multiplied together. I just need to write this in the next line here. X minus 1 minus square root of 3. X minus 1 plus square root of 3. And so you have these 6 zeros. Now, it is possible to solve this if we wanted to. We could sit down and multiply this times this, times this, times this, times this, times this. But for the purpose of the examples here, I just want to show that if I have these 3 in blue, and my degree is 6, that I must have the counterpart pieces. And then this is how we would write them out. The rational zeros theorem explains that there's a relationship between these two values and the zeros of a function if these are all real numbers. And in this case, these are all real numbers. So what we want to do is we want to take the possible factors of 4. So that would be, I'll just put possible factors of 4. Okay, so 1 and 4 are factors, and 2 times 2 is a factor. Then we divide by the possible factors of 3. So we take this thing and we divide by this thing, but we're not really dividing. We're listing the possible factors, and we're listing the possible factors 1 and 3. Now, we want to be careful because it could be that 1 is negative or it's positive. We don't know the specific value, so all of these have to have plus and minus attached to them. So we have to now divide all possible combinations of this. So what is 1 divided by 1? Well, that's 1. Negative 1 divided by 1. Negative 1. Okay, so then I have 2 divided by 1 and negative 1. So 2 and negative 2. 4 and negative 4. And now I have to take each of these things and divide by 3 as well. So that would be 1/3 and negative 1/3. 2/3 and negative 2/3. 4/3 and negative 4/3. Okay, so that means that all of these values are possible zeros to this function. And so you're thinking, I've got all 1, 2, 3, all 12 of these, and how on earth am I going to figure out which of these are going to give me actually 0 in this function? Okay, there's a few things you can do. Number 1, you could graph, but we're learning this to do by hand, so we're not going to graph. You could plug each of these numbers into your function and find out if the value is 0. Or you could use synthetic division. And so what I want to do is make sure you have these numbers written down. Okay, make sure you have these numbers written down. And I'm going to erase the board, and I'm going to use synthetic division with this, and I'm going to pick a random 0 and just start there. Okay? So hopefully you got those written down. So synthetic division, I need to remember I have 3, negative 11, but I don't have a piece in between these, so I need 0, 10, negative 4. Okay, and because 1 is simple, I'll do 1 first. Okay, so bring down the 3. That would be 3. 11 minus 3 is negative 8, negative 8, negative 8, negative 8, 2, 2, negative 2. So, does 1 work as a possible solution? A 0? No, it's not. So what I need to do is I need to retry another number. How about the next easiest number, negative 1? Okay, so that would be negative 3. So that's what, negative 14, positive 14, positive 14, negative 14, 10, that'd be negative 4, 4, 0. Okay, so I now know that negative 1 is a 0. It's no longer a possible, it is a 0 because it gave me 0. Let me just double check my work. 3, negative 3, negative 14, 14, 14, negative 14, 4, 4, 0. Okay, we're good. Now, here's the cool thing. I don't have to reuse this original piece anymore. I can use my factored form for the next division problem. I don't have to start over. I can just keep going with what I have. And so how about I do 2? So 3, 2 times 3 is 6. That's negative 8. Negative 8 times 2 is negative 16. So that would be negative 2. 2 times negative 2 is negative 4. That gives me negative 8. So that can't be right. So let's try negative 2. So that'd be negative 6, which is negative 20. Negative 2 and negative 2 times negative 20 is negative 40. This is getting big really quick. So, well, just to prove, negative 26, 26 times 2 is 52, and then that would be 48. So negative 2 and 2 both do not work. Okay, so let's try 4. Okay, so 3 times 4 is 12. Negative 14 plus 12 is negative 2. That would be negative 8. That would be negative 6. Let's see, negative 24. So that one doesn't work either. Okay, what about negative 4? Well, that would be negative 12. 14 and negative 14 and negative 12 is negative 26. Negative 26 times negative 4, is that going to get really big, or is that going to eventually cancel out? It's going to keep getting bigger. So now that I've checked all of my whole numbers, I need to begin to work on some of the fractions. Let's see. Why don't we just start with a big one? 4/3. So 4/3 times 3 is 4. So that would be negative 10. Negative 10 times 4/3 would be negative 40 over 3. So what I need to do is convert 14 into thirds. So what is 14 times 3? 14 times 3 would be 2, carry 1, 42. So that would be 14 is 42 over 3 minus 40 over 3. Minus 40 over 3 would be 2/3. Okay, well, what's 2/3 times 4/3? That's 8/9. Okay, so 8/9 and -4 don't work, and so we need to cancel that one out. It doesn't work. Okay, so positive 4/3 doesn't work. Let's see. How about negative 2/3? Okay, so negative 2/3 and 3 is -2, so that'd be -16. -2 and -16 is 32/3, but then this was 42, so that'd be 32/3. So that would be, what's 42 plus 32 is 74. Okay, this is getting bigger again, 74/3. It's getting bigger again and again, so that's not going to work either. So basically, you just have to check all of these until you get something that works. How about positive 2/3? 2/3 times 3 is 2, so that would be -12. What is 2 times 12 is -24 over 3. Well, that's -8. -8. So that'd be 6. 2/3 times 6. 6 times 2 is 12 over 3 is 4. So 4, 0. Aha! My next one is 2/3. So I have this piece left, and so what I'm going to do is just move this over because I was running out of room. So we still have 2 zeros left, and this should give us both pieces if we finish this out. So what other things have we not tried? How about no? How about 1/3? Let's just do 1/3 and see. 1/3, bring this down 3. That would be 1, -11. That's what, that's -11/3, and that doesn't cancel. Okay. Let's see. What about -1/3? So that would be -1, which would be -13, and that would just be 13 over 3. Well, that doesn't work either. So our last option is -4/3, I believe. So -4/3. That would be -4. That'd be -16, and that's what, 48/3. And so as you can see, this one didn't work either. So even though we had a power of 4, we only had 2 real roots. So sometimes you'll be able to find all 4, and sometimes you'll only be able to find some of them. And so this method will work for every polynomial where these are all real numbers.